Hello dear students, welcome back to the Wallah English YouTube channel guys. And in our today's session, we will discuss about the moment distribution method, which is another topic and the last topic of this particular fast track course series. Guys, we have already completed a lot of topic like static animacy, kinematic animacy, arches, ILD, truss, null force member, how we can find it out, right? So these type of title we have already done in our previous class. So guys, basically two lectures are remaining, this one and tomorrow we have another lecture in which we'll discuss the concept of moment distribution method only, right? So after that guys, your fast track course of the structure part is going to complete. Okay, so let us understand this particular topic guys, because we know that guys from this particular part you may find a lot of question in the gate examination, as well as you can see in the PYQ book you may see a lot of question was asked already from moment distribution method or displacement method. Okay, so let us start this particular session. So in this particular session basically we will try to cover the basic concept of displacement method first, then we'll discuss the distribution method, the distribution theorem, then we have fix and moment. In the basic concept, what are the topic, let me explain first. So guys, in basic concept we'll discuss what do you mean by stiffness. What do you mean by stiffness, right? Then what is the meaning of stiffness? What do you mean by relative stiffness? Relative stiffness. What do you mean by relative stiffness? Then we will discuss carryover moment and carryover factor, how we can find it out, carryover moment, carryover factor, as well as we will discuss the different sway condition, different sway condition, different sway condition. So these are the title which we want to discuss in this particular session basically, right? Or you can say that in two lecture we will try to cover it. So in today's session, first we will focus on the fundamental term or basic terminology, which is basically stiffness or relative stiffness, as well as carryover moment, carryover factor. So these are the title which we will try to discuss in today's class first. Now guys, we have already discussed the analysis of three-hinge arch. This particular part we have already completed in the previous class. You have already watched it, I know that, right? So let us start this particular class guys, and let us understand what are the topic which is required to understand any displacement method, or you can say that basically our moment distribution method. So what are the various topic which is required to understand this particular method completely? So first of all guys, you should know what is basically stiffness, what do you mean by stiffness, and how we can find out the stiffness, right? So this is very important part, because you may find 1 mark question which is related to this, right? So first one is stiffness, as well as we will discuss the relative stiffness, stiffness and relative stiffness. Okay, the second thing which we will discuss guys, or which is required, basically carryover moment and carryover factor. What is the meaning of carryover moment and carryover factor? What do you mean by it? Third thing is basically the fix and moments. What are the fix and moments we have? And you know that guys, these fix and moments will develop in the structure due to external loading as well as the settlement of support condition. So there are two reasons due to which fix and moment will develop in a structure. So guys, we will discuss that, how we can calculate it, what is the value of, or what is the standard values for the fix and moment. So these are the points which we will discuss. Then guys, we need to understand the distribution factor, distribution factor, what is distribution factor, as well as distribution theorem, distribution theorem. Okay, after understanding the distribution factor and distribution theorem, we'll discuss the different type of sway condition, different type of sway condition. What is the different type of sway condition we have, right? stiffness, relative stiffness, carryover moment, carryover factor, fixed end moment, distribution factor, distribution theorem, different type of sway condition, and in the last, you should know how to solve the problem by understanding all these topics. That is our main requirement or main outcome. So guys, in the last, you should understand how to apply this particular method to solve the questions. So if we did this particular things, guys, then definitely you are able to understand how to use the moment distribution method in the exam, right? Or how to solve the problem by using moment distribution method in the exam as well as in your practice or in your GATE test series also. Okay, so let's start with the first thing, which is basically the stiffness or relative stiffness. What do you mean by stiffness and relative stiffness? First, we'll discuss this particular point in detail. Okay, so let us discuss what do you mean by stiffness. So guys, let us suppose this is one of the member which we have, and I'm trying to apply certain force over here. Let us consider that force has a unit of, means a value of 1, or you can say that it is a unit force. So let us suppose if I am trying to apply the force which is basically unit force. So my question is, how much displacement will occur due to this particular unit force? That means, or sorry, wait a minute, yes, idhar aate hain bachcho, wait a minute, just try to understand these two things, then you are able to understand the stiffness term very well. Okay, okay, listen. Let us suppose right now you are trying to apply a unit force over here, and due to that unit force certain displacement will occur, right? Certain displacement will occur. Now just imagine, guys, just imagine, let us suppose if I am taking two different members, one is this, and let us consider second one is this, right? And I'm trying to apply the same force. Like in this case it is the unit force, in this case another unit force, but the displacement will occur in this particular member is little bit larger, and in this case it is little bit lesser. So can I say that it will have more displacement for per unit force, and this will have less displacement per unit force, correct? So the flexibility term, or the flexibility is nothing as, it is the force, it is the displacement caused by unit force. How much displacement you can cause by giving a unit force in a structure, then it is nothing as, it is basically flexibility. So guys, this is our first terminology which I want to explain, then we'll discuss this. So flexibility is basically what we can represent it by F. So what it is exactly? It is displacement caused by unit force. So guys, let us consider there is one spring which is to be like this, okay, and let us suppose I am trying to apply a force whose value is equal to 1. Now I need to calculate how much displacement is caused by this particular unit force. This particular thing is known as what? Flexibility. If more displacement, it is more flexible. Less displacement, less flexible, right? So guys, do you remember this particular relation? F is equal to K into X. What is K? Spring constant. What is X? That is displacement. So right now, how much amount of force we are trying to apply? It is 1. So can I write here Kx is equal to 1. So X is equal to what? That is basically displacement, and we need to calculate this only. So guys, displacement caused by unit force is equal to how much? It is equal to 1 by K, and this is nothing as, this is basically flexibility. So if it causes more displacement by 1 unit force, that is more flexible. If it is causing less displacement, then it is less flexible. Okay. Now guys, if we talk about the stiffness term, it is just opposite to this. It is just opposite to this. Now you can understand it very well what it is exactly. Now what is stiffness? It is the force required. It is the force required to give unit displacement, to give unit displacement, to give unit displacement. Force required to give unit displacement. How much force is required to give unit displacement? It is known as what? It is known as stiffness. Clear? So guys, again we will take the same structure, which is basically spring, and we can write here F is equal to K into X. Clear? Now force required to give unit displacement. How much force you need to give unit displacement? That means X is equal to 1. So guys, K is equal to how much? Sorry, F is equal to how much? It is equal to K. Then this is nothing as, this is basically stiffness of the spring or stiffness of the member in general. Clear? But in our structure, we'll not define this particular stiffness or like a linear stiffness term. We'll use the angular stiffness or rotational stiffness, right? So let us discuss what do you mean by rotational stiffness basically. Okay. Now let us come to this particular statement, right? What is written over here? The force required to give unit displacement is known as stiffness. This we have already discussed. Now guys, in our structure analysis, we need to understand what do you mean by rotational stiffness basically. It is the moment required, to give unit rotation at the near end. Now what it is exactly, sir? Let us discuss this. Okay. Moment required to give unit rotation at the near end. Moment required to give unit rotation at near end. And this is nothing as, this is basically our rotational stiffness. Okay, sir. Now let me explain how to calculate this. So guys, to calculate the rotational stiffness, we have different cases, right? When the far end is fixed, far end is free, far end is hinge, far end is roller, far end is guided roller, like this, right? And we will try to calculate how much stiffness is required for different far end condition. Okay. So let us understand the first case. When the far end is fixed, when the far end is fixed, then what should be your rotational stiffness? Let us understand this, and I will explain this particular definition in the first case, right? We'll discuss this particular statement in the first case. Okay. Let us suppose this is our hinge support or roller support, and this end is a fixed end. So guys, whenever you are trying to apply a moment, so that means whenever you are trying to apply some external moment, then that particular end is to be considered as a near end, where you are trying to apply some external moment or where your applied moment is there. So let us suppose if I am trying to apply the moment like this, so this value is basically M and it is applied moment. This one is what? Applied moment. Okay. So this end will become our near end. What it is exactly? This one is near end. This one is near end. Okay. And just opposite to this end, it will become far end. This will become far end. Let us suppose the length of member is L, EI is constant. Okay. This end is A and this end is B. This end is A and this end is B. So guys, we need to find out the stiffness or rotational stiffness of this particular member when far end is fixed. Now there are two terms of stiffness in this particular structure also, guys. One, from A to B you may have stiffness, and from B to A another stiffness term is there. But guys, we are trying to define the value of A to B when near end is hinge or roller, or where far end is basically fixed. Now let us suppose you have applied the moment, then what will happen? It is trying to deflect and it will generate some reaction. So let us understand this. This is hinge, this one is fixed. Now we are trying to apply some external moment M, and this is our deflected shape of the structure. Clear? Now you know that, guys, at this particular end theta is possible. Theta is possible. Let us suppose this is A and this is B. This is A and this is B. And I need to find out what is the stiffness of this particular member when the far end is fixed. Clear? So guys, to find this out, what we need to do, we need to calculate the reaction first. What is the value of VA? What is the value of VA? Let us do this. So we know that the net displacement at A is equal to how much? It is equal to 0. Now there are two reasons by which the displacement will occur at this particular joint. One is basically this moment M, due to which the beam is trying to deflect in this way, right? And this is our displacement. One of the displacement, let us consider delta 1. And second one is our external reaction, that is VA, due to which again displacement will occur like this, delta 2. Clear? Delta 1 and delta 2. Delta 1 and delta 2. Now guys, the net displacement should be equal to 0. We know that because at this particular support we have external support reaction, due to which this particular joint cannot move anywhere, and ultimately the net displacement value should be equal to how much? It is equal to 0. Clear? Now guys, you can see here, due to this particular M value, what will be the value of delta 1? It is ml square upon 2ei. Clear? ml square upon 2ei. And what about this this delta 2? Delta 2 is equal to VAL cube upon 3i. VL cube upon 3i. Clear? Now we know that guys, the net displacement value should be equal to how much? It should be equal to 0. So can I write here guys, del 1 plus del 2 is equal to 0. If del 1 plus del 2 is equal to 0, we can write here ml square upon 2ei plus VAL cube divided by 3ei, and it is equal to 0. So VAL cube divided by 3ei is equal to minus ml square upon 2ei. You can cancel this. You can cancel this one. So ultimately the value of VA is equal to how much? Minus 3m by 2l. So this is the value of reaction which we are getting right now. Minus 3m by 2l. Minus 3m by 2l. I hope this particular point is crystal clear to all of you. Clear? Now guys, we need to use the Castigliano's second theorem over here so that we can find out what is the value of this particular theta. How we can do it? It is very simple. How we can do it? Let us understand this. So guys, this particular value is M and we have VA, right? Let us take a section at a distance of x, so this is basically xx. Clear? Now I want to write the equation of moment at xx, which is equal to what? Plus VA into x plus m. Now what is the value of VA? We have already calculated it. It is minus 3m by 2l. Minus 3m by 2l into x plus m. Now, as per Castigliano's second theorem, you need to find out the total strain energy of the structure, right? So total strain energy of the structure is integration 0 to L mxx square dx upon 2ei. Clear? Now let us put the value. So ut is equal to 0 to L. We'll place this particular value, minus 3m into x divided by 2l plus m bracket whole square dx upon 2ei. Now guys, what we need to do? We need to take the derivative of it. As per Castigliano's second theorem, we can write here del ut by del m is equal to how much? It is equal to theta. Because as per Castigliano's theorem, if you find the total strain energy of the structure and take the first partial derivative of it with respect to the force or moment in the direction of that, you are able to get the displacement value. So in this case, we will get the value of theta. Clear? So let us calculate the value of theta, guys, by using this particular equation. So theta is equal to what? 1 by 2 EI, 0 to L, then take the derivative of it, 2 minus 3m by 2L into x plus m. Clear? Now further we will take the derivative of it with respect to m. So it will become minus x by 2L plus 1 dx divided by 2ei, that is outside the integration which we have written. Okay, no problem. Now guys, let us solve this further. Let us solve it further. So we can cancel this 2 to 2. So ultimately theta is equal to 1 by ei. Theta is equal to 1 by ei. Okay. Then guys, we need to write 0 to L as a integration limit. Then you need to multiply it. You can take m is also outside the integration part. So minus x by 2L plus 1 whole square dx minus x by 2L plus 1 whole square dx. Okay. So theta is equal to m by ei. Theta is equal to m by ei. Now integration 0 to L. This will become x square plus 4L square minus 4xL divided by 4L square. Then you need to write dx. You need to write dx. Okay, sir. So theta is equal to how much? It is m by ei 0 to L, right? Put it. So how much you will get? It is, okay, we need to integrate it, right? Let us write 4L square ei, and this is m by 4L square upon ei. Now you need to integrate this, then you have to put the limit. It will become x cube by 3, and this is 4L square into x minus 4x square L upon 2. You can cancel this, it will become 2. Clear? It will become 2. It will become 2. Okay, perfect. Now guys, let us use another page. So theta is equal to m upon 4L square ei. Now we'll put the limits. So at L, it will be L cube by 3. L cube by 3 plus this one is 4L cube minus this value is how much? 4L square. It is perfect. This one is perfect. Wait a second, guys. Just hold on. Just hold on. Yes. Now this value is how much? This value is 2L cube. 2L cube. Okay. Now let us solve it further. We'll get the value of theta. M by 4L square upon ei. Then this value is how much? L cube by 3 plus, wait a second guys, there is some mistake in the integration part, or either some value we have put it over here, right? Yes, there is one mistake, which is because this value is 3m into x divided by 2L, so we have missed this particular value. Sorry for this. This value should be minus 3x by 2L. This value we have missed. That's why we are getting a wrong value. Sorry for this, guys. Let us continue this particular solution from this particular point. Okay. So we have the value like theta is equal to m by ei integration 0 to L bracket minus 3x divided by 2L plus 1 bracket whole square dx. This is our equation. We'll use this particular equation. Let us write here. Let us write this particular equation. So theta is equal to m by ei. M by ei. Now we'll write integration 0 to L, and now let us open this particular relation. Okay, so it will become minus 3m plus 2L minus 3m plus 2L minus 3m plus 2L bracket whole square divided by 4L square dx. This should be our equation. This should be our equation. This should be our equation. Perfect. Now guys, theta is equal to how much? It is m by ei. Then you need to open it 0 to L. So how much you will get? We can write 4L square outside the integration. Now let us open this. So 3x plus 2L. So we'll write here 3x whole square. 3x whole square means 9x square, right? Plus 4L square minus 12LX. This should be our equation, right? And then you need to write dx. Okay, so theta is equal to m by 4L square ei. After integrating it, what you will get exactly? This value will become 9x cubed by 3 plus 4L square into x minus 12L into x square divided by 2. You can cancel this, it will become 6. You can cancel this, it will become 3. Now place the value of L over here. So theta is equal to m upon 4L square ei, and place this particular value, it will become 3L cube plus 4L cube minus 6L cube. Clear? So ultimately what term will be remaining over here? It is L cube. So we can write here guys, theta is equal to how much? Theta is equal to m upon 4L square ei multiply by how much? 7 minus 6, it will be L cube. Now you can cancel this. So what you will get exactly? Theta is equal to ml upon 4ei. Now the question is, sir, what is our stiffness? So as we have discussed, stiffness is nothing as it is the moment required to give unit rotation, right? So that means how much moment is required to give theta is equal to 1. So guys, m is equal to how much? M is equal to 4ei by L. That means this will be our rotational stiffness when the far end is fixed. Clear? It is 4ei by L. Kindly check this. 4ei by L. Understood? Okay. So when you find far end as a fix, so what will be your rotational stiffness from A to B? From A to B it is 4ei by L. And now you know that how to calculate this also. Okay. Just watch this and please let me know if you have any doubt regarding this particular concept. Any doubt regarding this particular concept, guys? Any doubt, any doubt, any doubt? Please write down. Crystal clear to all of you? Okay, perfect. Now let us take the another case when the far end is roller or hinge. When far end is roller or hinge, then what should be the stiffness of the member? Let us understand this. So this end is hinge and far end is also hinge or roller. You can take roller or either you can take the hinge also. There is no problem. So let me write here. This is hinge support and this one is also hinge support. Now you are trying to apply certain moment M. So what will happen? It is trying to deflect in this way, right? If you are applying moment M at the near end, then it is trying to deflect in this way. Let us suppose this is A, this is B, this is A, this is B. So what is the value of theta A which is caused by this M, and what is the value of theta B which is caused by this M which is present at A? So theta A is equal to ml upon 3i and theta B is equal to half of this value ml upon 6ei. Now the question is, sir, what is the stiffness when the far end is roller or hinge? So guys, in this case, the stiffness for A to B is equal to 3ei by L. Please remember this. 3ei by L is the stiffness. 3ei by L is the stiffness. I hope it is crystal clear to all of you how to get the value of stiffness when the far end is hinge also. Okay. Next one is when far end is free. When there is no support condition at the far end, then what should be the stiffness? Let us understand this. Now guys, if you apply any moment over here, then this particular member can rotate with an angle of infinite, right? So can I write here m is equal to what? K into theta. Now we know that theta is equal to how much? It is infinity. So k is equal to how much? It is m by infinity. So anything upon infinity is what? 0. So when far end is free, then stiffness is 0. Then far end is free, then stiffness is 0. Next one, when far end is guided roller. When far end is guided roller. So this is hinge and this is guided roller. Okay. So let us suppose if you apply the moment m, then it is trying to deflect, definitely, right? So let us consider this is theta. So in this particular case, the stiffness of member will be EI by L. When far end is guided roller, then the stiffness of member will be EI by L. Clear? Yes or no? Please write down, bacha. It is clear or not to each and everyone? Clear or not? When far end is guided roller, it is EI by L. Okay, perfect. Now guys, let us understand the another term which is known as relative stiffness. Now the question is why we are defining this, sir? If we already know the what is stiffness of a member, then why should we define relative stiffness term? It is very simple. It is very simple to understand. So in case of relative stiffness, what will happen? You are trying to eliminate the property of material, right? You are trying to eliminate the property of material from the stiffness terminology. Let me explain it first, then you are able to understand this. So guys, let us suppose if we have far end as a fix, then in such case, what will be your stiffness? 4EI by L. Now can I say that our stiffness is basically depending upon certain parameter. Our stiffness is depending upon certain parameter. This 4 can vary. It may be 3, it may be 1, it may be 2 also, like this. So guys, this particular constant is changing with respect to the far end condition. So it depends upon far end condition, right? Second thing, it depends upon value of E also. What is E? E is Young's modulus of elasticity, and this is the property of material. So property of material. Okay. Now I, what is I? Moment of inertia, right? Now this is the cross section property of member, or we will write property of member basically. I and L, property of members. Getting my point? So guys, it is understood our stiffness term will depend upon the far end condition, property of material, and property of member. Now if we talk about the relative stiffness, we are trying to eliminate the property of material from this particular term, and that's why we are defining the relative stiffness. Now let us suppose guys, in your question, if you are using the same material in the entire structure, then in such case it is better to write the relative stiffness in place of stiffness, because we know that we are trying to use the same material in all the member, right? So we can use the relative stiffness term in place of stiffness generally. So relative stiffness can be defined as K by 4E. This is the standard formula. K by 4E is the relative stiffness. Now tell me guys, when far end is fixed, then what should be the relative stiffness? It is very simple. What is our stiffness? Stiffness will be 4EI by L, now divided by 4E, right? You can cancel this 4E to 4E, and ultimately it will become I by L. Clear? When far end is hinge, so if far end is hinge, then relative stiffness is how much? You know that when far end is hinged, stiffness will be 3EI by L, and then you need to divide it by 4E. So how much you will get? 3I by 4L. Okay, sir. Next, when far end is free, so relative stiffness is what? 0, because we know that the stiffness of member is 0. That's why it is 0. When far end is guided roller, so what should be the relative stiffness value? We know that this value is EI by L divided by 4E. Now if you solve this, you will get I by 4L as a value. Crystal clear? What do you mean by relative stiffness? What do you mean by stiffness? I hope you are able to understand it very well. Okay. Now guys, the next thing which we need to discuss is basically what do you mean by carry over moment and what do you mean by carry over factor. What do you mean by carry over moment and carry over factor? So please remember this particular point. Let us suppose if your applied moment is in clockwise direction, this is basically applied moment, then the carryover moment will also be in clockwise direction. If applied moment is in anti-clockwise direction, then carryover moment will also be in anti-clockwise direction. And usually clockwise moment we will consider as a positive and anti-clockwise moment we will consider as a negative. Clear? As a negative. Now what do you mean by carryover moment, sir, and carryover factor? Let us suppose this is our beam in which far end is fixed and you are trying to apply some moment M, which is basically applied moment, and this particular structure is trying to deflect in this way. Now let us suppose this one is what? This one is our moment which is developed at the far end. So this end is B. Let us write MB, and this is the moment which is developed at the far end. So whatever carryover moment you have, that should be developed at the far end. Please remember this point. Okay. So guys, you can see here, if it is clockwise, then this is also clockwise. If it is anti-clockwise, this one is also anti-clockwise. So whatever end moment which is developed at the far end is known as carryover moment. Carryover moment. Okay, sir. Now let us take the case when far end is fixed. When far end is fixed, let us suppose this one is clockwise M. So guys, we will have another clockwise moment which is basically MB, and this MB is equal to just half of this particular value, which is our applied moment. Clear? This one is applied moment and this one is carryover moment. Carryover moment. Now guys, carryover factor is nothing as it is the ratio of carryover moment upon applied moment. Right? So what is the carryover moment over here? It is M by 2 and applied moment is M. So this ratio will become 1 by 2. That means the half of the moment which we have applied is, or you can say that the carryover moment or the moment which is developed at the far end is exactly half of the applied moment. That's why we are getting a ratio of carryover moment upon applied moment is equal to 1 by 2. Clear? That means please remember this point, carryover factor is nothing as carryover moment divided by applied moment. Okay. Now when far end is free, what will happen? When far end is free, very simple. This particular end is not capable to bear any moment. So the carryover moment value is equal to how much? 0. Similarly, carryover factor is how much? It is also 0. This one is also 0. Next, when far end is hinge or guided roller. So let us suppose you are trying to apply moment M. Then how much moment will develop over here? We can write here guys, MA is equal to 0 because this particular support is not capable to bear any kind of moment. So guys, in this case also carry over moment is 0 and carry over factor is 0. Clear? Now I am giving one question. When the far end is guided ruler, then please find out what is the value of carry over moment and what is the value of carry over factor. Do it by yourself. Okay? Okay guys. Now let's see the question part. Okay. This is first question. You need to tell me which one of the relation is true between stiffness and flexibility. So we know that stiffness is nothing as it is the force required to give unit displacement, and flexibility is nothing as it is the displacement caused by unit force. So guys, in this particular case we know that both are inversely proportional to each other, right? So that's why B is the correct answer for this particular problem. B is the correct answer for this particular problem. Next, the moment distribution method is fall in which particular category? It is basically a displacement method. The moment distribution method is best suited for which type of frame? Guys, mainly rigid jointed frame structures are used or is analyzed by using moment distribution method. So that's why the answer is B. The answer is B. Next, the ratio of stiffness of beam at the near end when far end is hinge and far end is fixed. So for far end is hinge, stiffness is 3 EI by L. When far end is fixed, so it is 4 EI by L. If you take the ratio of it, so it is equal to how much? 3 by 4. So B is the correct answer for the problem. Right? Now relative stiffness of a structural member of moment of inertia I and L is given by what? So you know that guys, usually the stiffness which we are trying to write is 4E by L. If you divide it by 4E, you will get I by L as a relative stiffness. So if in question it is not mentioned the far end is fixed or hinge or free end and etc. So what you will consider? Consider far end as a fix and get your answer. So C is the correct answer, guys. Stiffness of a prismatic beam whose far end is guided roller. EI by L. EI by L. Okay. So guys, this is all about for today. We'll discuss tomorrow the next thing, which is basically our distribution theorem and different sway condition. So these are the things which we'll discuss tomorrow, and tomorrow this particular series is going to complete, right? And I hope you are able to, it means you are enjoying this particular series, guys, and you are able to get some concept from here. Okay, so thank you so much for joining the session, guys. Let's meet tomorrow at the same time. Bye bye and take care, guys.